So it's a great pleasure to contribute to this Energy Future seminar series. I'm very pleased to be here. And as you heard, my name is Emilio Martinez-Paneda. I'm a senior lecturer in mechanics and materials here at Imperial College. And today I want to talk about material degradation challenges in offshore wind, hydrogen storage, and lithium-ion batteries. In essence, what I want to do is to show how the disciplines of mechanics and materials are at the core of the technological opportunities and challenges that arise due to the energy transition. I guess this is not a surprise because mechanics is everywhere and materials are the building blocks of technology, but I want to highlight some specific mechanics and materials challenges that we must overcome in a road towards net zero. For the sake of time, I will be rather superficial given the broad audience and the range of topics covered, but I'll be happy to go deeper into the science in the Q&A session. And I will divide my talk into three parts. First, I will start with the challenges associated with the hydrogen economy. Then I will move into lithium-ion batteries, and I will end up with offshore wind. And before I start, of course, very important to emphasize that the work that I will present is a collective effort, and I need to thank many people here, not only the PhD students and postdocs of my group, but also collaborators at Imperial and elsewhere, and I have listed some of them here in the slide. So let's get going. I'm pretty sure that all of you have heard now about the role of hydrogen in the energy transition. It's called the Swiss knife for decarbonization, as it can be used in many applications and sectors, including some that are known to be particularly difficult to decarbonize. So the interest in hydrogen as an energy vector is rising fast, expectations are high, and a lot of work is going on into transforming this hydrogen promise into a reality. You will have seen in the newspapers that governments are keen to exploit this opportunity, and large sums of money are being devoted to enable this technology. And one of the key issues is that this needs to happen fast, right? So there's an urgent push to deploy a hydrogen energy infrastructure that currently doesn't exist. So for example, the EU plans to deploy, I think it's 40,000 kilometers of hydrogen transport pipelines over the next 15 years. So this has led to a number of materials engineering questions, like how can we store and transport hydrogen safely and efficiently? For example, can we reuse the existing gas pipelines? And these questions arise because hydrogen has a dark side. It's flammable and it can significantly degrade metallic materials. And this last point is what I'm about to talk. We know since almost 150 years ago that hydrogen makes metals very brittle. As you can see in the slide, Johnson reported in the Proceedings of the Royal Society in 1875 about this phenomenon. He wrote about some remarkable and extraordinary decrease in fracture toughness and breaking strain of iron and steel in the presence of hydrogen. And it is true that how hydrogen interacts with metals is indeed remarkable and extraordinary. One of the effects that you will see when you expose metallic samples to hydrogen is a significant loss in ductility. What you see here are uniaxial stress-strain curves. So I just expose my samples to hydrogen, for example, to hydrogen gas, and then I pull, and then I see this stress-strain behavior. And you can see that as you increase the hydrogen content by, for example, increasing the hydrogen pressure, there's a very significant reduction in the failure strain. Another important effect is the reduction in fracture resistance that we see in the presence of hydrogen. You can see here that an alloy that fails at a fracture toughness of 150 megapascals square root meter will fail well below 40 megapascals square root meter as you increase the hydrogen content. And this is a low strength steel, but in high strength alloys, the reduction in fracture resistance can be of up to 90%. And I think this is a key point to emphasize. The susceptibility to hydrogen damage increases with the strength of the material. You see here fracture toughness in a given hydrogen-containing environment, so this is similar to seawater. And then you see that as you increase the yield strength of your material, your fracture toughness goes down up to the point that for these high-performing alloys, these high-strength alloys, hydrogen-assisted fractures occur at toughnesses that are below 10 megapascals per square root meter, so almost like a ceramic. We like metals because they are ductile, but hydrogen makes them very brittle. And I think this is important because what this picture is telling us is a two-way message, right? It's telling us first, hydrogen is compromising decades of metallurgical research. So we have developed high-performance materials, but we cannot use them. And the second one is that by using high-strength alloys, because they're very cost-effective, we are starting to see hydrogen-related failures in many applications and sectors where we never heard about before. So this hydrogen embrittlement phenomena is not a new thing, it's quite an old thing. So material scientists are very familiar with this. Traditionally, it was mostly a problem related to offshore engineering, right? So very aggressive environments where you have high hydrogen content. But now, as we use these high-strength alloys, these modern alloys, which are very cost-effective and we want to use in our buildings, in our bridges, in our cars, in our railways, we're starting to see hydrogen-related failures in many applications and sectors where we never heard about before. You can see this example here of the cheese-grater tower here in London, where the bolts were failing due to hydrogen embrittlement. So in very otherwise benign environments, we're seeing these hydrogen-assisted failures. And this, of course, takes me back to my main motivation, right? Given how susceptible metals are to hydrogen, you can imagine how challenging it's going to be to deploy this hydrogen infrastructure that we need in our road towards net zero. We're already starting to see accidents, and these are very early days. I mean, the technology is not even there yet, and you can see here already some accidents occurring. And you might wonder at this stage, okay, Emilio, how can it be that almost 150 years since Johnson's paper in the Proceedings of the Royal Society, those failures are not being prevented? We don't understand enough about it to prevent those hydrogen-related failures. I mean, there's multiple answers to that question. I guess one would be that it is a quite nasty and complicated scientific phenomenon. I mean, it is very multidisciplinary. It crosses the boundaries of mechanics, chemistry, material science. And we do know some things. We know the basics. We know that hydrogen atoms coming from an aqueous solution, hydrogen gas, any containing hydrogen environment will enter the material, will migrate fast through the crystal lattice, and will be attracted to areas of high hydrostatic stress or high volumetric strains, where the lattice expands and there's more space for the hydrogen to fit in. But then what hydrogen does here in this fracture process zone is complicated, and it really interacts with the material in many ways and at multiple scales. It can change the dislocation mobility, it can stabilize vacancies, it can reduce the bonding strength between metal atoms. So the physical picture is complicated. And this is one of the reasons why we're being precluded from preventing those failures. But I think this is something that we've been working on, and I think there's an opportunity now to develop models that can predict when hydrogen failures will occur. And I won't get too much into the details, but I'll just say that we have worked on 3 themes in order to be able to develop these models. The first one has to do with modeling coupled deformation diffusion phenomena. So we want to understand the critical variables of our problem, like the stresses and hydrogen content, how much hydrogen we have, where and when. We want to map those things precisely. We also want to develop a mechanistic understanding of hydrogen-assisted cracking. So I told you before that it is a complicated problem. Many things are happening, and we need to be able to apply some rationale, to do some clever experiments to identify what are first-order effects and what are second-order effects, because we will never be able to model a pipeline atom by atom, right? So we need to make some choices. And finally, of course, once we understand how the material behaves, once we have the right equations, we need to do a bit of computational science as well. We need to implement those models, we need to deliver those models, and we need to provide predictions at the scales that are relevant to engineering practice. And among these things, it involves modeling the initiation and growth of cracks, which is a challenging problem by itself. So let me elaborate a bit more on these topics without getting too deep. So the first one is the coupling between mechanics and diffusion. So we want to model the deformation of the solid. This is just essentially Newton's second law, so to say, in continuum mechanics. And this is Fick's law, so an extended version of Fick's law. So this is how hydrogen travels. So hydrogen will travel driven by concentrations, gradients of concentration, but also, as you see here, by gradients of hydrostatic stress. Hydrogen accumulates in regions where the volumetric strains, the hydrostatic stress is larger, so there's more space due to lattice dilatation. And this is, by the way, the simplest model that you can use for modeling hydrogen transport. In reality, hydrogen not only travels through the lattice, but it's also trapped in some microstructural features, such as grain boundaries, carbides, dislocations, and so on. So we have also developed more sophisticated models that account for those things. And then basically what I want to emphasize is the connection with mechanics, right? It is very strongly coupled. You can see here, this is the steady state solution of this transient problem. And you can see that the hydrogen content depends on this exponential term that includes the hydrostatic stress. So if we want to know how much hydrogen we have, which is key to determine when cracks will initiate and grow, we also need to know exactly what are the stresses. And the key point here, without getting into too many details, is that the critical distance ahead of a crack where hydrogen-assisted cracking takes place is only of a few microns. So these are the distances where conventional material models like conventional plasticity, like von Mises plasticity, break down. So you really need to enrich your constitutive description of your material to capture basically the mechanisms that are governing material behavior at those scales, which has to do with GNDs and plastic strain gradients. So we have done that. We have used these more enriched strain gradient plasticity models that better describe what is happening ahead of cracks near at that shorter distances. And basically what you see here, I'm plotting the stresses ahead of the crack. You can see that as you approach the crack, the stresses that you predict are much larger than those that you get with conventional models. And the same goes, of course, with the hydrogen concentration. You can see that you get much higher hydrogen content. So you really need to get these two right if you want to have a predictive model. That takes me to the second ingredient. So this is this mechanistic understanding of hydrogen cracking. And here the key question to answer is, how can it be that if I have the same material and that same material in air shows a ductile fracture process, so it fails in a ductile manner with these microvoids growing and nucleating and coalescence and so on. But if I put the same material in a hydrogen-containing environment, I see these brittle fracture patterns where you see cracks opening along the grain boundaries. And in my opinion, there's three key ingredients to understand this, why this is happening. The first one is that if you do atomistic simulations, like DFT, molecular dynamic, of those grain boundary decohesion, or basically fracture energy or surface energy degradation with hydrogen occupancy, you see that actually that if you have a lot of hydrogen, so if your grain boundary is full of hydrogen and an occupancy of 1, you see a very significant reduction on the fracture energies, a 40% reduction. So that's quite interesting. If my grain boundaries are full of hydrogen, they're going to be quite weak. So that could explain things. Of course, first of all, we need to answer the question of where are we in this x-axis, right? Are my grain boundaries going to be full of hydrogen, or are they going to be rather empty? Because if they're rather empty, there must be something else happening in there. And the answer to that comes from the chemistry. So we can take the thermodynamics of trapping based on Oriani's equilibrium, and we can plot the hydrogen concentration versus the binding energy, which is a measure of how energetically favorable it is for the hydrogen to go to that trap, like a grain boundary or a carbide. And then this is the trap occupancy. And you see that for strong traps, like grain boundaries, which are binding energies of -40 or smaller, with very little hydrogen, like 1 part per million, you can already see that the grain boundary is going to be full. So if you come back here, your grain boundary, you're always going to be moving in this regime, and your grain boundary is going to be quite weak. And this is, by the way, what they see in experiments. This is a very recent science paper where they use atom probe tomography, and you can see this thing in red is a grain boundary, and you can see that the grain boundary is full of hydrogen atoms, which are these red circles. So that takes me to the third and last ingredient. If you couple that understanding with the microscale plasticity models that I showed you before, what you see is that in the absence of hydrogen, the cleavage strength, so the strength at which you switch to brittle failure, is too high. Your stresses are not high enough, so they don't interact, and then you need other mechanisms. You need those voids to nucleate and grow and coalescence. However, the moment you bring hydrogen into the picture, then you lower the cleavage strength, these two lines cross, and automatically you have a model that is able to capture how you go from this ductile fracture process to a brittle fracture process with no fitting parameters whatsoever. You just tell him now hydrogen comes into the picture, and the model automatically is able to capture the shift from ductile to brittle. So that is great news, and that takes me to the last third front that we have been doing research on, which is to couple this understanding, these equations, into a robust computational framework. And one thing that is challenging from that perspective is that even if I know what drives cracking, I need to simulate the propagation on cracks, which is quite challenging. From a physical viewpoint, we will use something, what we call these phase field models, which is basically basically grounded on the thermodynamics of fracture. So fracture occurs whenever the energy released by your solid is sufficient to separate two surfaces. So you have a toughness, critical energy release rate of your material, and then you have the strain energy density, the energy that is accumulating in your solid and that will allow for a crack to propagate. And this is the foundations of fracture mechanics and Griffith's fracture mechanics. But the key thing is that from a computational perspective, it's not so easy to track how cracks propagate, because it's a complicated, in general, tracking discontinuities is a complicated mathematical and computational problem. So the idea is that but there's a very simple idea that we can exploit, this phase field paradigm that is quite convenient. So if you have two phases, let's say, for example, the crack is the red phase, and then the non-damaged part of the material is the blue phase, you can think of them as having a sharp interface, or you could also smear the interface such that you can describe these two phases by means of a phase field variable. And this phase field variable will take, for example, the value of 0 in intact material and the value of 1 on cracks. And just by tracking how this variable evolves, we can capture all this complicated cracking phenomena. And you can see it here. And by the way, I should emphasize here, I'm going to use the red color for plotting cracks. So every time you see red, that means a crack. And you can see this very complicated, these are two different time steps. You can see these very complicated cracking patterns occurring, crack coalescence, nucleation of secondary cracks, merging of multiple defects. So we can capture the propagation of cracks based on sound thermodynamics of fracture mechanics, and we have computational tools that will allow us to see how those cracks propagate. And there's only one thing left to do. We know that hydrogen makes cracking easier. We know that it reduces the toughness of the material. So how can we take that into account? I mean, the first step is straightforward, right? This is what the experiments tell us. The toughness of the material is sensitive to the hydrogen content. But quantitatively, how do I provide this relation, right? What is the function that I use? I think the good news is that the framework is universal, so you could do experiments and just fit with experiments. But we could also apply the mechanistic rationale that I mentioned before, right? So we can simulate the coupling between the formation and diffusion, so we know how much hydrogen we have. We use the trapping thermodynamics to know, as a function of the hydrogen that you have in the lattice, how much hydrogen you have, for example, in your grain boundary. And then you can go to these atomistic calculations that are done offline. And for a given hydrogen content, you know how much the fracture energy is reducing. So everything can be coupled in a quantitative fashion without the need for any fitting parameters. So that's quite exciting. So let me show you some results. These are what we call R curves, crack growth resistant curves. What you see here is the applied load, and this is the crack extension. And you see, a measure of the applied load. And you see basically the trend that you expect in the experiments. As you increase the hydrogen content, the fracture resistance of your material goes down. And what you see here is the influence of the loading rate. If you load very fast, then there's no time for the hydrogen to accumulate in the fractured region. So you again have higher resistance to crack propagation. If you load very slowly, on the other hand, then there's enough time for hydrogen to accumulate there, and then fracture becomes easier. And let me show also some quantitative comparison with experiments. You can see here, these are tensile bars of a pre-charged steel bars. I think it was, I can't remember what steel this was, but you can see that here, this is the notch tensile strength versus the hydrogen content. And you can see, of course, that it goes down, and then you see that the model agrees very well with experimental observations. And these are a set of a bit more interesting experiments. So these were done at SINTEF in Norway. They have a seawater bath. They introduce some samples. They have a notch, and each of these samples is subjected to a constant load, a different load. Each sample had a different load. And they were just waiting to see when cracking will occur. And their hope is that by one of the samples was charged to a load that was small enough such that you will never see hydrogen embrittlement, you'll never see failure, because hydrogen embrittlement requires a stress. So if the stress is low enough, then there's no issues. But as you can see, the symbols are the experiments. All of them failed at a relatively short time from an engineering perspective. But the good news is that we can take our model, we can reproduce, not only reproduce our experiments, but also run virtual experiments over very large timescales and decide or tell engineers what is that critical load below which they can load without embrittlement issues. And we can do anything. This is, for example, a very classic and complicated benchmark or standardized test to measure the susceptibility of screws, anchors, and bolts, which are typically very susceptible to hydrogen embrittlement because they're used with high strength alloys. And you can see that it involves steel into concrete beam material, but still there's no problem for these models. We can capture in 3D the complete failure of the screw. What is more exciting, I think, is that we can model large-scale 3D problems, and we can correlate our models with inspections. So you can kind of create this idea of a digital twin of critical infrastructure. So here you can see a pipeline containing multiple defects due to pitting corrosion. This has been characterized by Nicola Rosa and co-workers using non-destructive evaluation. And it's a 12-kilometer pipeline, but we choose to model a critical section of 3 meters that contains more than 100 defects. And we're not limited to model cracks, but we can model defects of any arbitrary geometry because we are solving for this damage variable, this phase field, as a degree of freedom. So let me show you a video so that you can see how things evolve. And you should start seeing here some defects start growing, coalescence of defects on the top and bottom, and then eventually those defects grow, merge with each other, and you have the complete failure of the pipeline. I mean, this looks a little bit like a video game, but I should emphasize that this is quite a sophisticated microscale or multi-scale multi-physics model. So basically, at the end of the day, we have a tool that allows us to know how the crack will propagate and when it will propagate. So we can decide when to replace the component or what are the limit service conditions. So before I was talking about the possibility of using the gas pipeline infrastructure to transport hydrogen. These models can be used to efficiently investigate the viability of this approach, right? So there's a lot of discussion about, okay, what pressures can we transport? What purity of hydrogen can we transport? And very expensive trials are now going on in Scotland, Germany, and other places. But these trials could be replaced by this kind of model, so at least optimize. I should say, we could probably optimize them to the very least. And finally, we have extended the framework to fatigue. We just need to add a fatigue degradation function, and we can then deliver predictions based on the material toughness, nominal material properties, and the loading history. For example, here you can see how we can produce what is called virtual SN curves with and without hydrogen, and we see a very good agreement with experiments. And we can also predict the influence of hydrogen on Paris law coefficients or deliver virtual SN curves for any geometry or loading history. And I emphasize that the Paris law behavior and the SN curve are an output of the calculation. That means a prediction and not an impact. And this is my last hydrogen slide, but I want to emphasize that what I have shown you before is only one side of the coin. I talk about models because models allows us to simulate any scenario, mapping regimes of safe operation and enabling the deployment of this hydrogen infrastructure. But to build those models, we need to spend a lot of time in the lab first. We need to understand how materials behave in the presence of hydrogen, and we need to make sure that our models reproduce what is happening in reality. So here you can see some of the equipment in our lab, in addition to our microscopy and mechanical testing facilities. And of course, you are most welcome to visit us and use it. Okay, so let me move now into battery degradation. And this part, I think, needs no motivation, as batteries are already a part of our daily lives. However, we want to go farther. We want electric cars that can travel long distances. We want phones and laptops with durable batteries. And we want to store the fluctuating output of renewable energy. And you know how batteries work. During charging, you have lithium ions traveling towards the anode. And when you discharge, the lithium ions go towards the cathode. And material degradation challenges arise as a result of this, and more specifically as a result of lithium intercalation. Because essentially you have lithium being inserted into these storage particles in the anode and the cathode, and this leads to a change in volume and to mechanical strains. And this continuous cyclic shrinking and swelling of these storage particles leads to the appearance of these cracks, which basically degrade battery performance. So our goal here is to develop models that can predict the nucleation and growth of these cracks and the resulting degradation of battery performance. And we want to predict this as a function of the material and charging conditions. We want to again map safe regimes of operation and inspect the viability of new material solutions. And when you look at the equations describing the physics of this problem, you see that they actually have many similarities with the hydrogen case. You are essentially solving a coupled deformation diffusion fracture problem. And the main difference is that the partial molar volume is 1 order of magnitude larger than in the case of hydrogen. So we have chemical strains that result from this lithium intercalation. And there has been a lot of work devoted to modeling the failure of single particles, usually single and idealized particles. But none of these works have accounted for fatigue for cyclic charging, which is basically what is happening. You have cyclic damage. They were all modeling a single charging cycle. So what we have done here, this is together with my Imperial colleagues, Willy Wu and Wei Long, we have extended those models to fatigue, and we have simulated the failure not only of idealized particles, but also of realistic particles with realistic shapes. And what we see is that we are able to gain insight into this particle cracking process, and we are able to map safe conditions of battery operation. For example, we can determine the critical particle size or the seed rate below which no cracking will be observed. On another front, and this is together with Adam and colleagues at UCL, we have gone one step further, and for the first time we have been able to model the entire cathode. And we do this by combining multi-physics phase field fracture models, similar to the ones you've seen before, with advanced X-ray computed tomography imaging. And this allows us to evaluate the influence of different phases, like binders or pores, and also explore the role of cell characteristics like electrode thickness, for example. Here a 2D section with the various phases and basically the fracture predictions. And these are 3D results showing lithiation, fracture, and basically showing how the electrode exhibits a highly heterogeneous electrochemical and fracture responses, which depend on the particle size and the distance from the separator and the current collector. So we have a tool that allows us to evaluate the electrochemical performance and damage behavior as a function of discharge rate, electrode thickness, and the cycling voltage window. And this is the last item of our battery work. We have also been working on solid-state batteries, which are arguably the next big disruption in battery technology. So replacing the liquid electrolyte by a solid electrolyte not only enhances safety, but also leads to superior energy and power densities. However, this breakthrough is being hindered by mechanical interfacial instabilities. You can see some of them here. Basically, these instabilities occur at the Li-metal anode electrolyte interface and lead to the death of the shell and the short circuit of the battery. In particular, the biggest problem one could argue is the presence of dendrites. So you have these dendrites here, these filaments here that originate at the interface between the lithium metal and the electrolyte, and then propagate into reaching the cathode short-circuiting the battery. You can see this pretty well here with this sketch and also these experimental images. So every discharge cycle, what you see is a stripping. That is lithium being removed and voids appearing, right? You see the voids here. And every charge cycle, what you see is plating. That means lithium being deposited and those voids reducing in size and occasionally becoming occluded from the interface. You can see this here. And understanding this voiding process is critical because when these voids form, they lead to local current hotspots, so to say. They're called current hotspots, basically near their edges. And these hotspots are small regions of high local current, and these current hotspots are basically acting as precursors for the nucleation of dendrites, which grow to cause cell death. So we have developed a model that captures the main physical phenomena and that can predict for the first time how voids nucleate and evolve and how this leads to hotspot formation. And without getting too deep into the details, I would say that the model has three main ingredients. The first one is vacancy diffusion, so we can capture surface and bulk substitutional lithium diffusion that within the lithium metal anode. The second one is the mechanical behavior of anode and electrolyte, and this includes the viscoplastic nature of lithium metal, so that allows us to capture creep effects. And third one, we can capture the annihilation and nucleation of vacancies, which is basically what governs the void evolution. And for this last ingredient, we make use of that phase field paradigm that I was presenting before, and that constitutes basically the backbone of all these models, as it allows us to track interface evolution. So you can see that all these problems have some similarities and some common roots. So at the end of the day, you are modeling something that is multidisciplinary, that crosses coupled physical phenomena across material science and chemistry and mechanics. And at the same time, you're always dealing with complex interfacial problems. So you need some computational tools or some methods to track those interfaces. So at the end, basically, this is what we solve for. So we solve a diffusion problem. We solve a phase field voiding problem. So we use the phase field to predict how the voids evolve. We solve a mechanical viscoplasticity problem for the lithium metal. And then we solve also an electric problem. And we model both the anode and the electrolyte. And we try to gain insight into voiding and the emergence of hotspots as a function of the applied pressure. So there has been for a long time argued that solid state batteries can become viable if we apply a pressure to them, and also as a function of charge and material properties, of course. So let me show you some representative results. You can see here how a single void behaves under stripping. As expected, the void enlarges along the interface. This is what you see in the experiments. And you can see here, so on the left I'm plotting the phase field, so blue is the void and then red is the lithium metal. And on the right I'm plotting the distribution of current density. And you can see how those hotspots form near the void edges and how they sort of enlarge as we go along with the voiding process. And in plating, you see kind of the opposite effect in a way. You are depositing lithium, so you are seeing how the void shrinks, again, as we see in the experiments. And eventually we even see void occlusion, which is something that has been also observed experimentally. And finally, let me show a more realistic scenario where we have multiple voids undergoing multiple cycles of plating and stripping. And here you can see as in the experiments, phenomena such as void coalescence or the shrinking of voids due to the application of pressure and creep deformation. So we can use this model to gain insight into the interplay of the multiple kinetics phenomena that are happening here, the diffusion, the creep, the annihilation of vacancies. And essentially at the end of the day, we have developed a tool that allows us to predict when these interfacial instabilities occur. And these interfacial instabilities are the ones hindering the commercialization of solid-state batteries. So we can define safe regimes of operation, and we can efficiently assess new designs and materials. And now let me go into the final part of my talk, offshore wind energy. And the truth is that we have seen an amazing drop in the cost of wind energy in recent years, and a massive increase in installed wind capacity, which is excellent news. However, I believe that as with all new technologies, we can do much better. So life cycle management of offshore wind is still at its infancy, one could argue, and this is evidenced by the short lifespan, so the service life is 25 years, and also by the fact that operation and maintenance costs are still 80% of the investment costs. And this is another pressing challenge because offshore wind farms are starting to reach the end of their service life. So what you see in the slide is Horns Rev 1, which is the oldest large-scale offshore wind farm in the world. It's managed and operated by Ørsted. This is in Denmark. It came online 20 years ago. This means that in 5 years, we need to decide what to do with this and what is the real service life of offshore wind farms? Is it really 25 years, or are we talking about maybe 40 years? And here, the key thing of what limits the lifespan is the corrosion fatigue of the support structure of these structural monopiles, which are made of structural steel. And let me explain the way in which the service life of these support structures is currently being determined in engineering practice. This is essentially done using what is called SN curves, stress number of cycles to failure curve. So this is the stress amplitude, and this is the number of cycles to failure. So what you do is you go to the lab, you take a smooth sample, and you test it under cyclic loading. You pull up and down, and then record the number of cycles, loading cycles that it took to fail. So you have 1 point here, and then you do this for multiple load amplitudes, and then at the end, you get all these data points, and you draw what is called an SN curve. And this is, you draw it, of course, in a conservative manner. And then you go to your wind turbine monopile, and then you see what are the relevant loading conditions to your structure, and therefore take the relevant stress amplitude, go into this graph, and determine how many cycles will occur before the failure of your component. And since you know the loading frequency at which this wind turbine is being subjected, then you can figure out the amount of time that it will take before it fails. And this gives you this number, for example, right? 125 years. Now, the thing is that corrosion makes these things worse. So you need to take into account for the fact that corrosion will enhance fatigue failures. So how do you account for that? Well, the way that is done now is by applying an empirical knockdown factor. So you bring down this SN curve, and you do it by a factor of 3 specifically. And you may wonder where this 3 comes from. Well, it is a very empirical and conservative estimate based on data from oil and gas, which is also not so relevant data because it's limited data and it's based on different conditions. But then you do the next step. So again, you go to the stress amplitude that you're subjecting your monopile, and then you get the life, and this reduced life is of 25 years. That's basically the process in broad terms. And this is, I think it might sound to you a bit arbitrary, but also the entire protocol is based on a number of assumptions. For example, we consider that the load amplitude is constant, but in reality we have variable loading patterns. We also assume that corrosion is taking place at all times, but in reality we alternate periods of protection and periods of corrosion. The wind turbines are not exposed to corroded environments all the time, they're protected. We also assume that we have uniform corrosion, but corrosion is often localized, so you have pitting and localized corrosion. Of course, time doesn't come into play here, there's no time. However, corrosion is a time-dependent phenomenon. And also we're using smooth samples, very simple cylindrical samples, but real structures have complex geometry, so you could think of a weld, for example. However, the thing is that replacing these empirical procedures with more mechanistic models is not an easy task. So you may say, oh, okay, Emilio, this is too conservative, or this seems too conservative, or this seems too empirical. Can we do better? It's not such an easy task, because corrosion fatigue is another complex and challenging scientific phenomenon. You can see the process here. First, you have corrosion pits that originate at the seawater electrolyte interface, the seawater metal interface. These pits grow, driven by local chemistry and mechanics, and eventually you have a pit to crack transition event, and fatigue cracks will go and propagate until the failure of the sample. And there are 2 challenges here. First is predicting the evolution of this complex morphology, the morphology of this interface. And the second challenge is the strongly coupled nature of this phenomena. So the shape of these pits depends on the local chemistry and mechanics. So they will grow faster if you have higher mechanical fields, or they will grow faster if they have a lower pH and so on. However, the local chemistry and mechanics are also affected by the shape of those pits. So this is a very strongly coupled problem, and you need to be able to resolve that interface evolution and all the physics that comes with it and the chemistry. And this is, of course, in addition to the challenges that are inherent to both fatigue and corrosion, right? I mean, it's not only a problem for wind energy. Corrosion is a problem it's still a problem for many applications and sectors, right? So only in the UK, it carries a cost of £46 billion per year. And it plays a big role in another sector that is a key for decarbonizing our society, which is nuclear energy, both in fission plant operation, also in nuclear fusion, and also in radioactive waste management. We want to make sure that these things don't corrode ever. And we have been doing some work on this regard with my colleague Mark Wehman here at Imperial. But basically what I want to say here is that corrosion has always been thought of a too complex problem to predict using computers. However, I do think that there's an opportunity now to achieve this elusive goal. There are 2 issues that we need to tackle: the multiphysics nature of the problem, so it crosses multiple disciplines, and also predicting the evolution of interfaces, so predicting this evolution of the corrosion front. And we have seen before that computers are powerful enough these days to model complex coupled physical phenomena. And we have also saw before that there's a new paradigm that can be exploited to easily track interfaces. What I'm talking about here is, again, this phase field paradigm that I mentioned before. We have used it to predict microstructural evolution, fracture, and voiding in batteries, and it seems to be a massive success, so why not use it in corrosion too? And I won't get into the details of the formulation, but essentially has two ingredients in the simplest form. The short-range interactions, that is the corrosion process, material dissolution, atoms detaching, which is captured by the phase field variable, and the long-range interactions, that is the diffusion of metal ions away from the electrolyte-metal interface, to capture the interplay between the activation and diffusion control corrosion. So the corrosion front is given by this variable that tells me if it's equal to 1 if we are in the metal, and if it's equal to 0 we're in the electrolyte. And let me just show some examples of what we can predict. This is a classic benchmark test known as the pencil electrode test. The problem is essentially one-dimensional. What you expect to see is this metallic bar corroding uniformly, and there are both experimental and analytical solutions for the case of diffusion control corrosion. You can see here some representative results. On the right is the evolution of the corrosion front, as given by the phase field, and on the left is the distribution of metal ions. So far away from the interface, at the edge of the electrolyte, the concentration of metal ions is 0, but as it races into the saturation concentration and eventually into a value of 1 inside of the metal, where there's no diffusion of metal ions. And you can see here the prediction compared with the analytical solution of the variation of P theft versus time, and you can see that we get a perfect agreement. And this shows how we can capture the competition between activation versus diffusion control corrosion, as we observe in the experiments. You can see in the left that if the corrosion current is small, then we see linear behavior, indicative of activation control corrosion. But as we increase the mobility coefficient, we move into the parabolic behavior, indicative of diffusion control corrosion, with electrochemical reaction at the metal electrolyte interface occurring very fast and leading to the saturation and the surface concentration of metal ions. And the right shows the corrosion, how the corrosion becomes faster with larger diffusion coefficient for a diffusion control process, as you would expect. Here you can see the case of a semicircular pit growing uniformly, and you can see that we get a good agreement with other numerical estimations. And now let me take you briefly to some of the core novelties of our work related to the coupling of with mechanics. The first one is the influence of the mechanical fields in enhancing corrosion rates, as argued by Goodman and many others. You can see how the equivalent plastic strain and the hydrostatic stress change the corrosion current density. This can be easily introduced through the mobility coefficient, and we validate our approach by simulating these C-rings experiments that are conducted at different loads. This is the result of our coupled mechanical, chemical corrosion simulations. On the right, you can see on the same scale how the corrosion defect morphology prediction agrees very well with experimental observation. We focus only on one pit, but we could model all of them. And on the left, you can see how our predictions of corrosion left versus time for different load levels compare very well with experiments. And another thing that we have done is to extend the model to account for the presence of a passive film and the film rupture and repassivation processes that are relevant to most material environment systems. What typically happens is that a passivation film is created that protects the metal from corroding, and this lowers the corrosion current density. However, at some point our strains are large enough, and then the film ruptures again, and corrosion is enhanced until the repassivation process begins. So it's a cyclic competition between straining kinetics and repassivation kinetics. And we capture this by means of two features. First, that we have a critical failure strain for the film within each cycle. And second, by enhancing, again, the mobility coefficient through a new parameter K, which governs the stability of the film for that particular environment. So let me show you finally what the model predicts with these enhancements. I'm going to simulate here the corrosion of a plate with a semi-elliptical pit subjected to a uniform displacement. And if we look first at the influence of the mechanical load, what we see is that the higher the applied load, the more localized the corrosion process. And this is in agreement with expectations because a larger hydrostatic stress will sharpen the pit and increase its length. Now let's see what happens if we change that film coefficient. What you see is that it results in a faster repassivation from left to right, because if repassivation is fast, then corrosion process is more localized. In fact, you can actually see that we naturally recover the pit to crack transition that we have been trying to simulate for ages, I think. And finally, some images showing what you all know, that once phase field is used, complex morphologies can be predicted, such as the interaction between multiple pits. And here are some 3D results to emphasize that it takes no effort to go into the 3D domain. So it's a very powerful tool, and we can finally predict the evolution of a corrosion front. This takes me to the end of my talk. hopefully with some time for questions. So let me finish with two main concluding remarks. The first one is kind of the bad news. So mechanics of materials phenomena are holding back the transition to net zero. We have hydrogen embrittlement compromising the deployment of a hydrogen infrastructure. Future developments and improvements in battery technology are being hindered by material degradation problems, and the competitiveness of offshore wind energy is held back due to our lack of understanding of corrosion fatigue. The second conclusion is a piece of good news, so to say, right? So we keep learning about the scientific phenomena, and we have developed mechanistic multi-physics models that can deliver predictions at scales relevant to engineering practice. So there are a number of opportunities here, because this can be very useful in accelerating the transition to net zero. For example, those models will enable us to map safe regimes of operation, improving competitiveness and safety. We can also use these models to develop new materials and solutions to the problems that I mentioned before. For example, we could evaluate what are the characteristics of a material that must meet for a solid-state battery to be deployed, to be viable. And we can very efficiently assess the viability and cost of decarbonization strategies. For example, we can numerically test what is the purity of hydrogen and the pressure of the hydrogen that we can transport in existing infrastructure to deliver heating solutions to a city, or carbon zero heating solutions to a city, right? That's all. I'm just gonna end by saying that all the codes that we have developed, we've used finite element packages, are openly shared, so you can find it in my website. You feel free to go download and play with them and ask any questions you may have. And of course, a big thank you to my sponsors for supporting this research, and to all of you for your patience. Thank you.
Thank you very much, Emilio, and that was an excellent presentation. So do please put your questions into the Q&A box, and we will get to as many of those as we can in the next 10 or 15 minutes. So Emilio, I don't know if you want to take a look at the questions that are in there so far, and see if any of those.
Okay, yeah, thank you so much. So the first one is from Sharon. Says, what implications does your modeling have for design choices and new material development for use with hydrogen? Thank you, Sharon. That's a very interesting question. So there's two things that we can do with the models, essentially, right? At the end of the day, we can use the models for a given choice of material and given conditions, we can map safe regimes of operation. So we can say, we have these gas infrastructure pipelines. We want to use these gas pipelines to transport hydrogen in a very efficient and economical way. How can we do that, right? And maybe I should stop sharing my screen. Well, I can leave it there. So what are the conditions? What hydrogen pressures and purity can we transport in those pipelines? So we can use our models to be able to basically map those conditions. So we can tell engineers, okay, these are safe regimes of operation, you can work in there. So for existing materials, the models can be used. Now the question comes, what if you want to develop new materials and new solutions? Well, the models bring some sort of insight, of course. For sure, they capture the interplay between diffusion and fracture and so on, but we're also working on more microstructurally driven models, where we can also take into account the influence of different microstructures. But we have used our models, for example, there's a strategy now being discussed about using traps. So I said before that, maybe I can go back to the slide. I said before that hydrogen not only travels through the crystal lattice, but it also likes to seek a certain microstructural features. So we can use our models to say, okay, what happens if we increase, for example, the density of carbides? How will this affect embrittlement? So we can also use our models to gain insight into the design of new materials. Yes. Thank you. So I go to the next question. I hope that answered your question, by the way. Please feel free to follow up. The second one is an anonymous question. It says, some studies have shown that adding a low concentration of oxygen to a H2 rich gas can mitigate embrittlement. Have you studied that? Is there a simple explanation? I recently came across some of these studies. We should in principle be able to model that. I mean, it's another diffusion problem that you're accounting for. Of course, you need to understand before you need to do some experiments to understand what is the coupling between oxygen and hydrogen, right? And I think the key point here is that for example, if you think of a grain boundary, we said that if the grain boundary is full of hydrogen, then it's going to be much weaker. But if that grain boundary is full of other species that are not so harmful for that grain boundary, then you're going to solve your problem. So in a way there has been a lot of work not only in relation to oxygen, but also, for example, in grain boundary engineering to say, okay, what if we don't leave space for the hydrogen to occupy? Will that fix the problem? And the answer is yes and no. So there's a lot of discussion going on. I mean, hydrogen is a tricky business, and the hydrogen atoms are, of course, very small. So they like to go wherever they want. So maybe I'll go to the next question. Feel free to follow up again. So Roger, what is the realistic timeline for commercial applications of solid state in the electric vehicle market? Oh, that's a good question. Maybe some battery expert like my colleague Billy Wu will be able to answer that better. I mean, there has been a lot of work being done in the solid state. I mean, solid state will, the development of a solid state battery will be fantastic news. So there has been quite a lot of work going on in that direction. Initially, we thought that the electrolyte was not stiff enough, and maybe if you use ceramic materials for the electrolyte, then you will be able to prevent those dendrites and those cracks from growing and from short-circuiting the battery. However, this has not happened. Even ceramic, very stiff ceramic electrolytes have not done the job. We still see those phenomena happening in there. And we have now, people have even tried now single crystals, and they're still seeing those problems. I've read in the news that some people are using, or some companies are coming up with some suggestions for solid state batteries. However, I think the challenge here is to have a lithium metal on the anode, and this is what is a bit more complicated. So you can do less well-performing solid state batteries probably now under certain conditions, but we're quite limited when we really want to exploit the full capability of solid state batteries. My hope is that the work that we're doing in modeling this phenomena and predicting this phenomena will tell us what material characteristics we need to deploy a successful, a viable solid state, all solid state lithium metal battery. And this, of course, we haven't done the numbers yet. There's one step that is missing in our model, which is to couple these hotspots with the formation of dendrites. But once we have done this step, we will be able to answer that question. And if that question happens to be a material that we cannot really produce, that humans cannot produce, then we will be in trouble. But hopefully there will be some room for material design there. And there's always people coming with very ingenious solutions using, for example, nanowires and things like this, right? So hopefully there will be a solution there. I'm pretty sure if you tell material scientists what characteristics they need to achieve, they're very clever people. They'll find a way. Let me go to the next one. So that's anonymous. What software packages do you use for the multiphysics modeling? Sorry if you said it and I missed it. Yeah, so I mean, I don't have a strong opinion in this regard. I typically just use whatever tool does the job. But some of the codes that we have developed have been developed using commercial packages like COMSOL or Abacus. And we also use open source packages such as Phoenix. So it depends a little bit on the problem and what we want to simulate. And I can give you my opinion about the difference between them, but I probably shouldn't do that publicly. I have a good relation with salesmen from both companies, so I won't say much about it. Frederick, thank you, Frederick. He says, hi, Emilio, thank you for the insightful talk. I have a general question. Why would we still use metallic pipes prone to hydrogen embrittlement and relative to, for example, polymer composite pipes? That's a very good suggestion, Frederick. Thank you for your question. So there has been, back in the day, when pipes were thought not to be used in terms of hydrogen economy, but in other applications which are maybe more aggressive in terms of the environment, there were national labs in the US that were promoting this idea of using composites and polymer pipes. However, that didn't turn out to work so well. So hydrogen is a tricky business. Metals are particularly susceptible to hydrogen, but hydrogen also degrades all the materials, including composites. Things have changed a little bit since then, so the kind of applications that we're thinking are slightly different. So maybe those gaseous environments that we're thinking about are not so aggressive. And there has been a lot of work, and I heard of leading people in the composites community that are now putting all their eggs in the hydrogen basket and trying to get funding to come up with new exciting ideas along this regard. So I don't necessarily say no. So most people will tell you, well, we tried before, it didn't work, but there's new exciting ideas coming from the polymer composite community, and I think there'll be opportunities to maybe consider other material solutions for sure. Thank you, Frederick. Sharon, is this type of material level modeling already been applied in the industry for hydrogen batteries with energy? If so, has it been successful in predicting real-world full system performance or cost outcomes? That's a very good question, Sharon. So these deployments are relatively recent. I like to believe that I'm young. However, we have industrial partners that have approached us and that have used this code. So, for example, we have partners in the oil and gas business where they're looking at hydrogen embrittlement in very aggressive environments, so cathodic protection, H2S, and they have, I know for sure, they have been using our models to basically complement their experimental insight. But we have also been recently approached by companies working in the hydrogen gas or hydrogen energy sector. So we have a contract starting now with EPRI, for example, and we are working now. We are about to sign another contract with Tenaris. So there's quite a lot of interest now in these models, and based on the experience that we've seen by applying them to more complex conditions like oil and gas, I'm confident that we will be able to gain very good insight and rather precise insight. So I'm optimistic about the future, but I will be able to tell you a bit more in some months from now, because we'll do a bit more of this real scale modeling. There's an anonymous question about how binding energy affects the embrittlement and the scope of solid state hydrogen storage. Go back to this map. This is basically what we want. There's kind of a dual effect, and there's a bit of a discussion there, right? So this is Oriani's equilibrium, which is perfectly valid for most scenarios. And then here you have the lattice hydrogen concentration as a function of the binding energy, and this is the trap occupancy. So now the thing is, okay, for a given binding energy, what is the hydrogen concentration? So for a given hydrogen concentration and a given binding energy, what is the trap occupancy? And this can play in two ways. So if you have, for example, failure occurring at your grain boundaries, and you believe that your mechanistic interpretation of what's happening in hydrogen embrittlement is that the grain boundary is basically popping up, is the cohesion process happening at the grain boundary, then it's important to know the binding energy of those grains, so depending on the grain characteristics, because that will tell you for a given environment, a given hydrogen content, how full your grain boundary is. And then you will come here and you will see how much it has been degraded, basically. What is the fracture energy of the surface energy degradation with the hydrogen content? And then the other side of the coin is people that are trying to argue that maybe we could use traps in our favor, and this is the idea of a beneficial trap. So you could use, for example, carbides. Let's say, assume that carbides are not involved in the fracture process. So then just say you could put a lot of carbides into my material, and if those carbides have a strong binding energy, then they're going to be full very soon. So the hydrogen is going to like to go there. So the smaller the binding energy, the more energetically favorable is for the hydrogen to go there. So those strong traps may help in attracting the hydrogen so that the hydrogen doesn't go to fracture regions like grain boundaries, for example. And there's a comment by Michael Road. I hope that answers your question. Again, please feel free to follow up, where he says that polymers have mostly a problem with permeation losses. Thanks, Michael. And I think I managed to cover all of them on time, but feel free to shoot any other questions if you wish.
Great, that's brilliant, Emilio. And how can people get in touch with you if they want to, or how can they find out more information about you and your group?
Yeah, they can always visit our website, or feel free to contact me or follow me on Twitter or whatever they want. I'll be happy to reply to any emails or other further questions that you may have, or any comments, or if you want to collaborate, we're always happy to. We're always looking for exciting ideas and exciting projects. So very much looking forward to hear from you. Thank you.
Brilliant. Well, thank you again, Emilio, and thank you to everyone who joined us today. So next week's webinar has been postponed due to industrial action by the Universities and College Union, but we will be back on the 24th with a look at energy applications of particulate soil mechanics with Professor Catherine O'Sullivan. Catherine's from the Department of Civil and Environmental Engineering, and you'll find all the details on our website. Thanks again, everyone, for joining us, and I hope to see you again.